Hello, everyone. Hope you all had a good Thanksgiving. Um, this week, it's probably the last week of our lecture, and we have spent a whole semester to talk about energy systems and how to analyze energy systems and the emerging topics such as AI and the big data for clean energy transition. So we are aware of many of the different models or analysis on energy systems using data-driven analysis. Excuse me. And today we will talk about the limitations of models. This is very important because only if we are aware of the limitations of our analysis, we have better chance to interpret our models or our results more appropriately. So we will discuss some topics. As usual, we will talk about sample analytic questions, such as how do I know if I should trust the model and its results, especially when you read papers, news. How do you have a good sense of if this is a model you can trust? And what are the methods to address uncertainties? Uncertainty is very unique and very important, and sometimes it will decide our modeling results. So it's helpful for us to discuss uncertainties and how to address them. What are the emerging topics to improve integrated assessment models or IAMs? Integrated assessment models are some of the mainstream models that provide the analysis to support IPCC results, for example. And many governments, institutions, international organizations use IPCC results to guide their policy. And what are the limitations of IAMs, and what are the emerging topics that are discussing how to improve the performance of IAMs, how to interpret modeling results to communicate our models effectively. And all in all, after this class, you will have chance to use models, and you may ask yourself where to use model and how to build the model and what to say about your model. I hope this lecture will offer you some insights or discussions on those questions. I'd like to start with an example. Here, as you can see, it listed the projections of energy consumption in the United States, different projections by different institutions, governments, research organizations. Each line represent one projection in the 70s up to 2000, right? And especially important because that's during the energy crisis, and in order to guarantee the supply of energy, the government and the research institutions, they all needed to prepare for future demand, right? And now we know what actually the energy demand is in 2000. So you can compare the projections with the 2000 historic actual demand, you may find that the projections tend to overestimate the energy demand. Many things, different things happens. Technology advancement, energy efficiency improved, energy intensity decreased. So the energy consumption per unit of GDP decreased. Also because energy saving and other measurement to really reduce the energy consumption. The price, the market also played a role. This is a great example for how modeling or modeling-based projections can went off. One other example, more recently, right, in the past decades, we discussed that the cost of renewables really decreased by a magnitude of an order of a magnitude. And that's not well incorporated even in the world best modeling team. These projections by IEA, which is an international energy agency, each year they publish a flagship report, World Energy Outlook, and you can see each line represent their projections of solar and wind installation capacity. This is cumulative installation capacity. And each year, they tend to underestimate solar and wind expansion. So even for the world best modeling team, still underestimates the demand. But science models tend to do better job. Here, as you can see, this is a fascinating story about Exxon oil company in the 70s or even 50s. They did a internal projection about future carbon dioxide concentration and related temperature rising. So as you can see, their projections now for 100 years, right? Now we are in the 20s. So the concentration reached about 420 ppm, and the related temperature change is about 1.1 degrees C. That's very close to what's really happening over up to now, as you can see. So this is fascinating how science projection can be so powerful in the sense using the models. And the right picture shows assessment of the scientific models, and each of these represent projections by different scientific groups and models, and compared to the observations, which is the real historic observations. And as you can see, the temperature and the concentration are very close. This again shows scientific models are doing better job comparatively. So we will explain why. So there are conditions for model robustness. That means if model perform well, it has to rely on several conditions. So models can be accurate when they describe systems that are observable and measurable. Temperature is measurable, it's observable. Concentration of carbon dioxide, that's measurable and observable. And the x-bit constancy of a structure over time. We know the concentration of carbon dioxide mostly from the consumption of fossil fuel and land use, land cover change. X-bit constancy cross variations in conditions not specified in the model. This is more complicated, but the Earth systems are comparatively show x-bit the constancy, right? Also permit the collection of ample data. For the scientific analysis, we rely the measure data. Now we have satellite data. We have more methods to collect more than enough data to do those analysis. So for our scientific modeling efforts, it shows very great robustness. But for socioeconomic, that's rely on many different moving pieces, and the performance of models are comparatively less accurate, because socioeconomic development can have structure changes. That means our modeling results rely on core data and assumptions, and those assumptions are very often based on historic experiences, and those historical experiences can be off if there is a structural change. And even we know there's a structural change. For example, we know in the future we might have breakthrough in fusion technology. But the timing, the exact timing and the characteristics of a pivotal events or technology change is unpredictable. 50 years ago, we project that in 50 years, we might have fusion technology, and which is today, right? But today, if we project it in 50 years, we may have breakthrough. Someday, the technology might have breakthrough, but we don't know exactly when. This is just an example. Another example I will share is structure change. For example, the shale gas revolution in the United States. Here is a chart shows the new power generation capacities each year. As you can see, prior 2000-ish, coal generation has a larger share of the new capacity. And after that, what happened? You can see natural gas capacities really dominate the new generation capacities. So what happened is the shale gas revolution, driven by the technology breakthrough of horizontal drilling and hydraulic fracking. These two technologies are very important because without horizontal drilling, we have to do vertical drilling, and that's very cost. Now with horizontal drilling, you only use one vertical well, and then you can use horizontal drilling to reach far larger area to extract the natural gas or shale gas. And fracking is to break the rocks so the gases can release to the well. Those are technologies that enable the shale gas revolution, because conventional those gas reserves, not resources, not reserves, because they are not economic extractable. Now with the technology breakthrough, that changed the structure, and it makes natural gas cheap and competitive. And natural gas has many advantages, right? It more flexible, it's cleaner than coal, and if it's cheaper, it becomes default fuel for power generation during that period. And starting from about 2010, as you can see here, more capacities of renewables are catching up. That's another structure change, is renewable costs getting cheaper and become competitive. So those structure changes really change the landscape of the power sector, and that's not predictable if we discuss the power generation in before those changes, right? Because we know it might change, but we don't know when, and now it has changed, and we have to refine our models and redesign our models to incorporate those changes. I discussed the underlying drivers of these structure changes, the cost of renewables and the cost of natural gas really shape the landscape. So that brings, when we discuss models, there are challenges. That's so-called mission impossible, is that we need to predict the unpredictable in some cases. I prefer use projections because the models not really predict the future, rather it projects the future given certain conditions or certain assumptions. And the priceless for the model really, especially if we model the socio-economic system, price or costs really have are the fundamental assumptions which drive the results, right? And we put a price tag on certain things. For example, we discussed the idea of a social cost of carbon. What are the damage costs of a 1 ton of costs? That all depends on how we value things, even how do we value human life, which is already very controversial, right? Because how human value priceless, how do you really put a price on it? That's the mission impossible to price the priceless. But we discussed there are different ideas, approaches to try to put some numbers, such as statistical value of life and other advancement in the social cost of carbon. So the drivers we model has uncertainties, and it's the convention that we should have better modeling, better tools to model uncertainties. Here are some steps or ideas to how can we better incorporate uncertainties, define an endpoint of analysis. That means we need to build a boundary of analysis. If it's very important to have such a boundary, so we know where are our uncertainties, so we can list all uncertain parameters. Those parameters can be cost, can be technology, can be other parameters, and specify maximum range of values. So we know the range of certain values. For example, cost. Maybe we don't know exactly what's the cost, but maybe we can build a range of values of the costs. That will help us to specify the probability of the distribution of the values. So each parameter, we can build the probability distribution, and using methods such as Monte Carlo simulation and other simulation tools, we can determine and account for correlations of the parameters and the results. And we know the probability of distribution of the parameters. Now adding together, we would know the probability distribution of model results or predictions. So that way we can quantify the uncertainties, and if we still uncertain, we can add more data and repeat the analysis if needed, so we can better sense of uncertainty. That practice should help us to really understand the sensitivities of uncertainties and how each parameter contribute the uncertainties. Even in corporate uncertainties, still there are many challenges. I mentioned the integrated assessment model team or community that very often those models rely on physical science to build the model and make assumptions that price signals will for sure take actions or put out recommendations for climate actions that not necessarily translated to policy change. There are examples of why those models might missing represent the reality. Let's say the model results can be optimistic about renewable energy development, but there are risk-averse investors that, because they already invest heavily on fossil fuel, so there's investment and infrastructure inertia to move their investment to renewable energy. And subsidies to the fossil fuel industry is huge, and that also disincentivize the development of renewable energy. Carbon lock-in, including technology lock-in. Once we have a technology and the infrastructure to support those technologies, we kind of lock in the system. And there are other factors such as inequality, public opinions, even you have the political view, how that translates to citizens' actions, their confidence in political institutions, trade and investment, global supply chain disruptions, competence of government, and different level of supply, and those are interesting examples of why the integrated assessment models or their results can, when they really have a reality check, some of the recommendations might not seem feasible or sounds reasonable. So here is a paper by a group of integrated assessment modelers trying to improve the modeling community, that they introduce the public opinion, for example, in the United States, because US has now been very hard for the federal government to take climate legislation before the Inflation Reduction Act. So many states have state legislation, and different states have different public opinion how they support climate action, or how the public believe in climate change, right? Using those public opinion survey, it indicates how public support climate action, and that would increase our understanding of how climate actions have better chance to succeed in each state. And then the paper compare the cost of a state approach to with federal approach, and they found the cost, because different states have different support, and some states have better chance and less cost, and so overall the cost not seems too off. So it provides an alternative approach that yes, federal legislation is preferred, but state approach can also contribute, can also make a difference. And now we have a federal level legislation, and still different states can contribute to the process. And this is a great example of how to incorporate political economy in modeling to enhance the performance of our models. If there are so much uncertainties and challenges, why we need a model in the first place? As you can see here, we use model to describe a system, to explain the relations, to do some experiments, how the changes of parameters would lead the change of the results, and also providing a source of analogy that we can use the model to communicate and educate stakeholders. So to provide some focal objects for scientific dialogue or policy discussion. Sometimes it can even be just a sort of experiment and help us to think through strategies and impacts, and it can provide the projections that help us to make decisions that are based on some evidence supported research. So models can do many good things and help us to think and to simulate. So that brings that we should focus more on modeling for insights, not on specific results. So how to build a model, we have to think about what research questions we are going to address, and modeling the elements, structure, and relationship that help us to think. If we got the results, we know the limitations and the uncertainties of the results, so we would not overinterpret or misinterpret our results. We would need to communicate the assumptions, the data, and the limitation of the models. We have showing this quote again and again, right? All models are wrong, but some are useful. We are trying to build a useful model, not a perfect model. And we know the limitation and the problem or the potential uncertainties of those models. So one example to focus on the structures and the relations is the Emerald's model provided by MIT. It tried to incorporate the essential drivers of our energy systems and carbon emissions. And by moving the parameters around, you can see how each measures will contribute to the concentrations of carbon dioxide and how it will change the temperature rising. So those practice rather provide some insights and how each of these efforts can really make a difference. And that's what we really need. So we need aware of the modeling limitations. We know some unknowns that's within our awareness. For example, cloud. If we model the climate system, we know clouds, ocean mechanisms, and there are some measure uncertainties that we are trying to improve. There are also unknowns because the Earth systems, the socio-economic system, is so complicated. It's really possible that there are omission of factors that we haven't aware yet. That means when we think about modeling, we need to aware of those knowns and unknowns, and try to find data and structure that can represent the system to avoid the garbage in, garbage out. Otherwise, the model cannot provide sufficient confidence that can help us to understand the system. So we also need to think about how to interpret the results that make sense, because results are outcomes of assumptions and how we structure the models. Results also does not automatically translate to policy. So be careful when you try to provide policy, because the results lead to policy change that can have other political reality and socioeconomic check. That means we need to communicate the limitations and uncertainties of our models, and that will help the policymaker to think. Sometimes the decision might be political. Sometimes the decision can be shaped by other factors rather than the model or modeling analysis. To help communicate and build the trust, the modeling community has pushed for the open source movement, that the model and the code needed to open source the data, open data, and open results, so it can create a space for open validation and comparison. So different models can learn from each other and compare and validate and build up from the shoulder of the giants, right? so we can even open source the efforts to validate the model and collect further data, the so-called citizen science, to involve in the contribution of this community. Model has a purpose, right, to help the society to make better decisions, to understand our challenges. So how to ensure a model for social good? We have some ideas that we need to mind the assumptions, to aware of those assumptions, and the model results are very often driven by the data and assumptions. Mind the hubris, mind the frame, mind the consequences, mind the unknowns, and the questions not answered. Mind the questions are not answered. Also, we talked those points before, but here really to bring them together, we need to pay attention to those factors. So we know the limitations and communicate them to make sure the model has a purpose and help improve our understanding, to enhance our evidence. So to summarize what we have discussed, models have limitations, and we need aware of those limitations that help us to use the model and appropriately and communicate the modeling results effectively. To focus on modeling for insights, and in the end, we hope that through evidence-based modeling practice, we can use the analytic tool for social good to help us to communicate and build the consensus among stakeholders and build the collective actions that needed to address the grand challenges we face. That's the purpose of using the model in the first place. And I hope this class help you to have a basic understanding of those ideas. And there are some fascinating examples. So if you are interested, please read more from the readings and cited work. I definitely encourage you to explore on those ends. So that's all for this semester. And I hope you enjoy the class so far. I know it's challenging through the online class, but I hope we learn from each other, and I really appreciate your efforts to do the assignments and to read the extended reading, and to build yourself, get yourself familiar, get your hands dirty in building the models and the analysis. And those are what will make the difference, and those will help us to have better modeling capability. Thank you all, and I wish you the best for your future study or future work. Feel free to get into touch if you have questions, and thank you.